Okay, class. So, as I mentioned, thermometer actually working based on the thermal equilibrium principle. So, how does it work? Okay, you can imagine that when you have thermometer, you place it under your armpit and so on. And that is actually thermal equilibrium between armpit and your thermometer, right? Okay, so the heat flow from thermometer and your body to thermometer will be different until it achieves thermal equilibrium, which means there is no net heat flow, keyword class, no net heat flow between these two objects that in thermal contact. Okay, so that is how you remember to write your keyword, no net heat flow, and then another keyword here is the temperature is equal, right? Which means the temperature that recorded by the thermometer is actually the temperature of the patient. Okay, so this is the first thing. Now we have two types of thermometer. One we call it laboratory thermometer, another one we call it clinical thermometer. Okay, so laboratory thermometer we use mercury. We use mercury as the liquid in the thermometer, and then clinical thermometer we use alcohol. If you really compare alcohol and mercury, actually alcohol is much more sensitive towards the heat, and the expansion rate of alcohol is much greater compared to mercury. Okay, but then we know that alcohol can evaporate easily. Temperature more than 70 something is actually evaporate, and then we don't have the liquid to measure the temperature anymore. That's why we use mercury here as the temperature. The range of measuring is actually greater. So how do we calibrate? Let's say I have a brand new thermometer that not yet calibrate. Let's say this is one. Very original thermometer. So I have this thing, I don't have any scale in between. I just give you this thermometer and then I ask you to do the scale. How are you going to do that? Of course you are going to put in ice water, right? Ice water, pure ice water is 0 degrees Celsius, and pure steam, okay, is 100 degrees Celsius, right? Steam is 100 degrees Celsius. Let's say I put this thing into a ice liquid. So I found that okay, it is the length of it is 10 centimeter. This is for the ice freezing point. Okay, so the temperature, the mercury will rise to 10 centimeter, where this is 0 degrees Celsius. Then I put it in steam. Okay, and then I found that the mercury continue to rise, and then the height of it, let's say, is 110 centimeter. Okay, so 10 centimeter, 110 centimeter, this is easy, very easy to determine what is a scale, right? So 110 minus 10 is 100 degrees Celsius. So in between you draw 100 line, that is every line will indicate 1 degree Celsius, right? That is how we calibrate temperature from original thermometer. Okay, so now I have another question to make you understand better. Let's say, okay, this is thermometer. When it is at a freezing point, it is 2 centimeter. Let's say 2 centimeter. Freezing point, it is 2 centimeter, and when it is boiling point, it is 24 centimeter. So this is boiling, 100 degrees Celsius, and this is 0 degrees Celsius. And then after the calibration of this thing, I put this thermometer into a cup of coffee, let's say, and then the temperature that's shown here is actually it rise up to, okay, so 24, it rise up to 10 centimeter. So can anyone tell me that what is the temperature of this cup of coffee? Okay, so you please tell me the answer. Whoever that can post the answer in your fastest rate, you post it. You are the first one that post it, and then you get it correctly, I will give you a limiting merit lah. Give you merit 10 mark. So class, solve this problem. Okay, that's how we calibrate thermometer. So there's another things that we said that not only mercury or liquid that can expand in terms of their volume, right? We can actually use wire to determine the temperature also. We call it temperature. Okay, thermocouple thermometer. Let's say I have a liquid here is 0 degrees Celsius, and this one is 100 degrees Celsius. Okay, question number 2, merit question. Okay, I have 2 wire here. One is copper wire, another one is iron. Okay, and then in between I have millivoltmeter. So if the temperature is different, it will show reading because there is energy flow. So this is also, we call it a thermodynamic property. Okay, so we know that this is 0 degrees Celsius, this is 100 degrees Celsius, and then the reading when it reaches 0 degrees Celsius is 10 millivolt, let's say, and then when it reach wait, let me think, it is 4 millivolt. Okay, it is 4 millivolt. Wait. Sorry. So when this is 0 degrees Celsius, 100 degrees Celsius, the reading here is 10 millivolt. So I would like to ask, what is the temperature if I put one of the end of this side to, I don't know what is the temperature here, and then I found that the answer is 4 millivolt. Can you please tell me the temperature of this liquid? Okay. So this is question number 1, and this is question number 2. So class, I would like you to try this, and then you can understand better how to calibrate. There is no specific formula here, you just go by ratio. Okay, and another calculation that we need to do is about the specific heat capacity. Okay, we know that this is energy that provided equal to mc theta. This is energy. This is mass. Okay, this is a specific heat capacity. Which means the energy that needed to increase 1 degree of Celsius of substance. Okay, and then this is the changes of temperature. Okay, so different material, it has different value of C. So if you look at the unit here, Q equal to mc theta. Q is energy, so it is joule. M is mass, so it is kg. C is the unit that I want to find. So theta is degrees Celsius, right? Degrees Celsius. So what is the unit for C then? The unit of C will be equal to joule kg -1 degrees Celsius -1. Right? -1 means that it is divided by. Okay, so the unit for C is this one, which means you need this much of energy to increase 1 degree Celsius of substance, and then that substance must be 1 kg. Alright, so let's say water. What is the specific heat capacity of water? Okay, for water, it is 4,200 joule kg -1 degree Celsius 1. Means that if you want to increase temperature of water by 1 degree Celsius, let's say you have a cup of water, 25 degrees Celsius, you want to increase it to 26 degrees Celsius, the energy that you have to supply here must be 4,200 joule to make it increase by 1 degree Celsius, provided that this is 1 kg of water. So you get an idea roughly what is specific capacity. If the specific capacity value is very high, means that this is a very good absorber. Okay, very good absorber because it can contain a lot of energy. Okay, to increase 1 degree Celsius, you need this amount of energy. So you can imagine that that's why water is always very hot, because the energy content is quite high compared to copper. Okay, so copper, chemical word, copper, C for copper is actually 390 joule kg -1 degree Celsius -1. Means that if you want to increase this ketolan cuprum copper by 1 degree Celsius, this is 1 kg of copper, you want to increase it by 1 degree Celsius, let's say from 20 degrees Celsius to 21 degrees Celsius, you need 390 joule of energy. So which one is easily get heated up? Copper, right, compared to water. Okay, so it means that this is good heat conductor. So when it get heated up easily, means that it get cooled down you want to cool it down also easily compared to water. So you have to remember that water actually very difficult to heat, to get heated up and also to cool down, because the specific heat capacity of the water is very huge. Okay, now Q equal to mc theta is the formula that you get, and then Q equal to ml is latent heat. This is energy, this is mass, and this is specific latent heat. Actually, everything in your note, I hope that you can really tidy out your note, and including all the calculation that I showed it here, you have to copy it in your notes lah. Okay, class, you have to really show me your effort. Okay, so what is the unit? Energy is joule, and then this is kg, and what is the unit of for L? Will be joule kg -1. Energy that needed to change one state, 1 kg of substance from one state to another state without the changing of temperature. You see that the temperature is actually no, we didn't really mention about temperature here. So that is what we call specific latent heat. Okay, so how to do calculation? I will show you one very simple example. Okay, saying that I have 2.5 kg of water. Okay, 2.5 kg of water, and then I want to change the temperature. It is initially 32 degrees Celsius. I want to change the temperature to 82 degrees Celsius, and then the specific heat capacity of water is actually 4200 joule kg -1 degrees Celsius -1. So what is the energy that I need to supply to increase the temperature here to here? Easy. Q equal to mc theta. So your M is 2.5. Come down. Your M is 2.5. C is 4200. And then degrees Celsius will be 82 minus 32. So you get final answer. What is the final answer? Okay. You get it for yourself, huh? So it's very easy. You just substitute all the things in your formula. Okay. Now I show you another example. Okay. So if the energy that supply here, or write Q, energy that supply here is 5.4 times 10 to the power of 4 joule, and then I have steel. Okay, I have steel that 600 gram. Okay, so the mass of steel is 600 gram. And then the change of temperature is from 20 degrees Celsius to 220 degrees Celsius. Okay, so what is the specific heat capacity of the steel? Okay, so you see that Q equal to mc theta again. So 5.4 times 10 to the power of 4 equal to, this one remember to change to kg. 0.6, C I don't know, changes 220 minus 20. So I got C, right? So that is how you get specific heat capacity of certain thing. Specific capacity is just like density. It won't change if this thing is still the same density, same purity. It is the same thing. It has fixed specific capacity. Okay, so it's just like if I have pure gold, the density always the same. I have pure mercury, the density always the same. So it is the same thing here. So this is a basic calculation, and then specific latent heat. Okay, specific latent heat. Okay, example, I have 200 gram of ice at 0 degrees Celsius, and then I want to melt it and then change it to liquid. Just now it's ice, huh? Now I want to change it to liquid of 20 degrees Celsius. And then specific heat capacity of water is 4200 joule kg -1 degrees Celsius -1. And specific latent heat of ice is 3.34 times 10 to the power of 5 joule per kg. Okay, So you can actually, if you draw it out, you can understand better, then you draw it out lah. So from 0 degrees Celsius of ice, you go to 0 degrees Celsius of liquid, and then from 0 degrees Celsius of liquid, and then you go to 20 degrees Celsius of liquid, right? So from here to here, we use Q equal to ml. This is latent heat. From here to here, we use Q equal to mc theta. So the total energy that you got to supply for the changes is this one plus this one. So the total energy here will be ml plus mc theta. So your m, remember to change it to kg. L is 3.34 times 10 to the power of 5 plus 0.2, and then 4200, and the changes of temperature is 20, and then you get your answer here. That is the energy that needed to change to make the whole changes. Okay, class, I hope that you can do it better, understand better by practice more. Question is attached in your note. Try hard to settle all. Okay, so I will continue. We probably have another two classes for this chapter that I would like to explain more about theory, because there are great scientists that involved in this theory, and then we will go through also to a very specific experiment for this thing. Okay, that's all, class. Thank you.